So before we start, any questions?
Yeah.
Any questions about the lectures, about the homework and the exams? Okay. So if no questions, we can start here. So we're gonna in today's lecture, we're gonna continue to talk about mass transfer coefficients, and we spent 2 lectures so far on this topic, and today we're gonna conclude this lecture, and if we have time, we will move on to the next topic, which is we're gonna do a review on thermodynamics, okay, which will be a very brief lecture. And after that, we're gonna move to the kind of the core part of this course, which is the single stage equilibrium, and then we're going to talk about different some typical and important separation operations, and then most importantly the distillation. Okay, so in Monday's lecture, we basically introduced the concept of additive diffusion, which is kind of a new mechanism of mass transfer when we have a system that has turbulent flow and eddies, right? And this mass transfer mechanism, well, basically it behaves similar to molecular diffusion, right? When we have a flow flowing across a solid surface in the direction that's perpendicular to the solid surface, there's no bulk flow, right? And in this case, for an example with only laminar flow, then you will have only in the direction that's perpendicular to the solid surface, only mass transfer mechanism is molecular diffusion if you have a laminar flow. However, if you have a turbulent flow, then you'll have eddies, right? You'll have eddies, and these eddies will, the velocity in the eddies will fluctuate. That will mix the species in near the surface. That will create an additional mass transfer in the normal direction to the solid surface. And this mass transfer is much faster than molecular diffusion. Mathematically, it behaves similar to molecular diffusion. So that's why we can use a similar equation, right? We know for molecular diffusion, we can use Fick's law to compute the flux, and by multiplying diffusivity with the concentration gradient. And now with additive diffusion, we can compute additive diffusion by adding another diffusivity term that's called additive diffusivity in order to include the effect of additive diffusion. Right? Conceptually, we can do that, but in reality, it's difficult to get additive diffusivity. That's why we again we resort to mass transfer coefficient concept, and we hopefully we can compute the total flux by multiplying the mass transfer coefficient with the concentration difference between the surface and the bulk of your fluid. Right now, in order to find out the total flux, we just need to find out the mass transfer coefficient, right? In last lecture, we talked about the way mass transfer, how we find mass transfer coefficients for a stagnant film and for a laminar flow. In this case, we have a turbulent flow. In order to find the diffusivity, we have to basically look at the analogies between the diffusive mass flux, heat flux, and a momentum flux, right? And that's what we did. When we write down the equations for mass flux, for heat flux, and for momentum flux, and we find there are some inherent similarity between these equations, among these equations, and these similarities further evidenced if we use dimensionless concentration or dimensionless temperature and dimensionless velocity, right? if you define such a dimensionless quantity and you plug in back to these equations, and we find out, actually, the mass transfer coefficient, heat transfer coefficient, and the Finney frictional coefficient, they are kind of related by this equation. Okay. And because we know for Finney frictional coefficient, we can compute it as long as we know the flow condition. We know the geometry of the tube, and the Reynolds number. We can compute the Finney frictional number. So that just hints us that if we further simplify this equation to some extent, maybe we can find the mass transfer or heat transfer coefficient from the Finney frictional coefficient. Then that's what we did. So we first basically look at the Reynolds analogy, right, which is kind of a very simplified analogy in which by assuming the momentum diffusivity is equal to mass diffusivity equals to momentum diffusivity, and all the added diffusivity epsilon d h m are the same, we can simplify this equation to this equation, which is called Reynolds analogy, right? In this case, as long as you can get the Finney frictional coefficient, then you can compute mass transfer and heat transfer coefficient, right? And this is kind of a good starting point, although in order to derive the Reynolds analogy, we made some very strong assumptions, which is that all the added diffusivity are equal, and all the momentum thermal and mass diffusivity are equal, right? Which is typically not true. So, but nonetheless, this analogy analysis just gave us a method for us to really relate Finney frictional coefficient with mass transfer and heat transfer coefficient, right? As long as we can further, we can derive a version that's more practical or more accurate, and that's what did by Chilton and Coben. So they, based on a lot of experimental evidence, they found that the Finney frictional factor, which is called the momentum J factor, equals to is related to heat transfer coefficient by this term, right? This term is defined as the heat transfer J factor, and it's also related to the mass transfer coefficient by this term, and this term is defined as the diffusion mass transfer J factor. Okay, and these are like empirical correlations from experiments, right? So they are not derived from rigorous mathematical theory. They are more like people done a lot of experiments. They got a lot of data, and they find this empirical correlation between the Finney frictional factor and the heat transfer and mass transfer coefficient, right? So the J factors here depends on the geometric configuration and the Reynolds number, right? That's where you have the Prandtl and the Schmidt number gets to play. And this Chilton-Coben energies are reasonably accurate if you have Prandtl and Schmidt number in the range of 0.5 to 1. Okay. So here is basically, there are exact mathematical forms can be derived based on the condition, right? For example, for a flow through a straight circular tube, the J factors, the momentum, heat transfer, and the mass transfer J factors, they equal to this, right? So it depends on Reynolds number. And then the same with other flow conditions, right? These are from your textbook. You can read the details here. But overall, we can make a plot in which we can plot the J factor with respect to Reynolds number on a log plot, right? And then all these parallel dependence becomes a straight line on this plot. So then you can, when you solve the problems, you can always, first specify the flow condition, right? What's the geometry of your channel and what are the Reynolds number? Then you can go back to this figure or go back to these equations and find the J factor. Then you can find the mass transfer coefficient. Then you can compute the mass flux. Okay. So that's all about the mass transfer coefficient. So far, we've talked for in the case where we have a flow across a solid surface, right? So far, we talk about you have a solid surface, then you have flow, by the surface, right? And we know that in the direction that's parallel to the flow, typically we define that as x direction. Then bulk flow is a major mechanism for mass transfer, but in the direction that's perpendicular to the solid surface, which is z direction, depending on if you have concentration gradient or if you have eddies, then you could have molecular diffusion or you could have molecular diffusion and eddy diffusion or both, right? Then we can use mass transfer coefficient to compute the mass flux in the z direction. So next, we're going to talk about mass transfer across a fluid interface, right? Which is different from the case here. We are studying the mass transfer flux at the liquid, solid, or fluid or gas solid interface. Okay. So in the case we have two fluids in contact with each other, right? These two fluids can be two immiscible liquids, water and oil, or it can be one gas phase and one liquid phase, right? In this example, for example, in this plot we have a gas phase that is in contact with a liquid phase. Then in order to solve the mass transfer problem here, the theory, one theory is called Fiume theory, which basically assumes there's a resistance, there's a stagnant thin film at the boundary, at the interface between the gas liquid phase. Right? There's a stagnant liquid film at the interface, and this stagnant liquid film will pose a resistance for the mass transfer, for A to goes into B or for B to come out, right? So now, in this case, if we assume we have a gas diffuse into a non-volatile liquid B, right? So we have a flux of A going into B. Meanwhile, since we have a non-volatile liquid B, the flux of B get out. This is negligible, right? Once A diffuse into B, it will be basically absorbed by B. Okay? And if we assume there's phase equilibrium at the gas-liquid interface, right? So that's at this Z equals 0, this interface. Then phase equilibrium basically here means that the concentration of A at the interface is proportional to the pressure of A or partial pressure of A in the gas phase, right? And typically we use Henry's law to relate that. And in the liquid film, we're gonna have a concentration profile of species A, right? In this case, we assume there's a linear concentration profile here. And because there's such a concentration gradient, then there will be molecular diffusion happen, right? That bring A into the bulk of B. And we assume there's well-mixed bulk region, which means in the bulk region of liquid, in the liquid, there's no concentration gradient of A. And in the bulk region of the gas phase, there's no partial pressure gradient of A. Okay. Now let's look at how we can solve this problem. So here, based on those assumptions, we can get NB is 0 and NA is constant with Z. C is constant. So if we neglect bulk flow, right, that's kind of simplest case we can do, then the total flux of A is made of only the diffusive flux of A, and that can be computed by the Fick's law, right? And then we can apply the concept of mass transfer coefficient, in which we approximate the derivative, this derivative, the concentration gradient or mole fraction gradient, by the ratio of the concentration difference divided by the thickness of the film, right? And we can also write this equation in terms of mole fraction. Then we can define a mass transfer coefficient to be the ratio of diffusivity by the film thickness, right? Then now this problem, we can, as long as we can find the mass transfer coefficient, then we can solve this problem. For the case where we have to account bulk flow, and in this case, then we have the total flux is made of both the diffusive flux and the convective flux, right? And the convective flux is mole fraction of A multiplied by the total mole flux, right? And in this case, again, because NB is negligible, that help us to greatly simplify this equation to this form, right? We've derived this before. And now we can just approximate this derivative with similarly, like here, like what we do here. We can approximate this derivative with the ratio of difference. Okay, but now slightly difference between these two examples here is that here, because we have 1 minus XA at the bottom, then when we approximate this, we have to first take this term into the differential, right? So that gives us CD AB D 1 minus XA Z, right? So we have minus sign disappeared because we just take it into the differential. Oh, sorry. Then we have 1 minus X here. Right. Then we know that if you do the integral, this gives you the log. And then when you compute the difference between two log, right? It becomes and you can just sum them together. That becomes the ratio of 1 minus XA at the bulk divided by 1 minus XA at the interface, okay? And then if we define the log mean of 1 minus XA to be this term, right? This is just mathematic definition. And if you plug in this back here, that will help you to simplify this equation to be the form where you have CDA over delta over 1 minus XA LM, that's log mean, multiplied by the mole fraction difference, right? And this has a similar functional form of this equation. Then you can just define a modified mass transfer coefficient to be the whole term here, right? And this whole term equals Kc, that's the mass transfer coefficient here, divided by 1 minus XA's log mean, right? Now you can solve for the mass flux of this problem if you can find out Kc prime. Okay. So usually the film thickness delta is unknown, so we have to go after a correlation for mass transfer coefficient. And the film series is often not very accurate, but it's widely used nonetheless. So one simple, for this particular problem, one simple start is to apply Chilton-Coulomb analogy to find out Kc. But since the film series not very accurate, there are, other series that further, make additional assumptions trying to really mimic what is really happening in this, in this liquid film, right? A liquid interface. One such model is kind of like the schematic of such model is here. That basically assumes, now we have a gas liquid interface. Instead of having in the film theory, we assume there's a film at the interface between the gas phase and the liquid phase, right? But in this model, we have an interfacial region, right? We don't have a film, we have an interfacial region. And then below underneath this interfacial region, we have a well-mixed bulk region, right? Well-mixed means there's no concentration gradient in this region, okay? And in this model, it assumes there are pockets of fresh fluids arrive from the bulk to the film. So that is to say, we have, small, pockets of fresh fluid. They move to the interfacial region, right? Then they will stay there for some period of time until they are replaced by some new pockets of fresh fluid, right? And now to solve this problem, we just solve the diffusion problem into this interfacial region, and this is similar to the diffusion to an infinite slab, right? But only for a short residence time of Tc, right? That's the time. Tc is the time, how long the for such a pocket of fresh fluid they will stay in the interfacial region, right? So and we've solved this problem before, so I'm not going to go into the math, but you can read your textbook. So the conclusion here is that this model is called Higby model, that assumes that there are fluid parcels moving from the bulk region of your liquid bulk region to the interfacial region, right? Where it will in the interfacial region there will be diffusion of component A or species A in this interfacial region. So there will be concentration profile in that interfacial region, but the fluid parcel will stay only in the interfacial region for a time interval of Tc, then it will move back to the bulk, right? So there's constantly replacement of your fluid parcel. So with that model, the mass transfer coefficient is going to be a function of the square root. It's going to be dependent on the square root of diffusivity of A divided by the kind of this interval time, and depends on what the fluid condition. You can have bubbles, droplets, or packed tower. Then this Tc will be different. Okay. Then there's another model that's called surface renewal model. And compared to the Higby model, here the assumption is that in Higby model, we have a pocket of fresh fluid moving from the bulk of your liquid to the interfacial region. They stay there for the same interval of Tc, right? In the surface renewal model, it just assumes the residence time for the fluid parcel in the interfacial region is not a constant. It's not Tc. It's a function. It's a distribution, right? So in that case, and it assumes that all fluid parcels are more likely to be replaced by young parcels, right? So in this case, mass transfer coefficient is still going to be proportional to the square root of the diffusivity, but now you have a S, that's the rate of surface renewal, right? So basically S, if you compare these two functional form, S has the unit of 1/Tc, right? And as long as you can get S as a function of something, you can solve for the mass transfer coefficient. Okay. Okay, questions? Now, so far we've talked about the thin film theory, and it's kind of the modified thin film theory in which you have interfacial region. But in reality, when you have two fluids in contact with each other, if you have a liquid film in the liquid phase, then there's supposed to be a gas film in the gas phase, right? That's more, that should be more like, real. So then the two film theory just assumes we're gonna have two films, on both sides of interface. For a gas liquid phase, we're gonna have a gas film in the liquid gas phase. We're gonna have a liquid film in the liquid phase, right? And in the fumes, there will be concentration or partial pressure gradient. So you have mass transfer happening due to molecular diffusion. At interface, still you have equilibrium. So the ratio between your partial pressure of A in the gas phase at the interface is going to be, proportional to your concentration of A in the liquid phase. Then in the bulk, you will have no concentration gradient, right? So this is idealized picture. You have more realistic picture. First of all, you don't have linear concentration or partial pressure profile, right? That's very, very simplified picture. Meanwhile, you don't have discontinuity, right? Here you have a discontinuity here. You have discontinuity here, right? A more realistic picture will have a smooth concentration or partial pressure profile in the liquid and the gas phase, right? While all the other assumptions are same. Now, this two film theory, there are some additional assumptions in order for us to derive the mathematical equation to solve for the mass transfer by applying the two film theory. First, there are no reactions at the interface. Secondly, there are phase equilibrium at the interface, right? So, and Henry's law applies. That means whenever we have phase equilibrium at the interface, there's partial pressure of A in the gas phase is proportional to the concentration of A in the liquid phase. That's like, they have a contact resistance, right? Because if there's no contact resistance, then they are the same. They should be equal, right? Then Henry's law, whenever you apply Henry's law, we know Henry's law is only valid when you have a small range of XA and YA, right? Then there's no bulk flow. So the total flux equals to the diffusive flux, right? This is valid when you have your total flux of A and B is very small, negligible, or you have equimolar counter diffusion. So the total flux of A basically equals the total flux of B, but they happen in the opposite direction, so they cancel each other. Okay. And there's constant total mole fraction C. Now, with those assumptions, we can write down an equation for the total flux in the gas phase. That's going to be can be computed by the gas phase mass transfer coefficient multiplied by the partial pressure difference between the bulk and the interface, right? Similarly, in the liquid phase, the total flux is proportional to the mass transfer coefficient multiplied by the difference of concentration in the bulk and in the at the interface. Then we have phase equilibrium that's described by the Henry's law. So note there are multiple different forms of Henry's law, right? You could have HA, that's the coefficient, multiply with XA or divided by CA, or other forms. But mathematically, it just means that the concentration of A at the interface is proportional to the partial pressure of A at the interface in the gas phase, right? Although different forms will have the Henry factor will have different units. Now we have three equations, right? In order to solve for an A, we have to get rid of some like parameters we don't know. here what we can do is we can just compile to eliminate the interface composition, right? What you do is just to, from this equation, you can derive PAI, as a function of other parameters, right? Basically, here PAI is going to be PAB minus NA divided by PAI, KP. Right, so just move KP to the left, then move PKB to the left. You have this, right? Similarly, you can get CAI to be CAB. Here we have plus NA divided by KC, right? Because we don't know the interface partial pressure or interface concentration. Now we just rearrange these two equations. We get this. Now you just plug in PAI and CAI into Henry's law, right? Then you will have NA, right, on both sides of the equation, right? You just need to rearrange that. Then divide all the coefficient, all the coefficient of NA to the other side of the equation. You will have this NA to be dependent on this term, which if we make some definitions, we can simplify this form to make it similar to what we are more familiar with, right? Now, if we define KL, right, if you define this whole term, 1 minus, so if you define KL to be 1 divided by this whole term, then you define this to be CA star, right? Then you can simplify this equation to be NA is proportional to this KL multiplied by a concentration difference, right? That's kind of a similar form we have to compute mass flux using mass transfer coefficient, right? So KL is kind of like an overall mass transfer coefficient that depends on Henry's law fact coefficient, the mass transfer coefficient in the gas phase, and the mass transfer coefficient in the liquid phase. Then CA star is like a fictitious CA in equilibrium with PAB, right? So because now we are, CA is HA multiplied by PAB, right? So it's like a fictitious concentration in the liquid phase, but in reality, it's the partial pressure of A in the bulk multiplied by the Henry's constant. Okay. Now, if we can find out the mass transfer coefficient Kp, Kc, and we find out the Henry's now coefficient HA, then we can compute the mass flux by using this equation. Okay. So there are several variations of this equation depending on the situation. So if we are going to compute the total flux using the liquid phase concentration, and the functional form will look like this, where you have Na equals KL multiplied by the concentration difference, right? Where you have Ca defined by this, KL defined by this. We can also compute the total flux with the gas phase concentration, right? In this case, we're going to have a different overall mass transfer coefficient Kg. That's this, and multiplied by the partial pressure difference. Okay. And you can also use, instead of using concentration difference or partial pressure difference, you can also use the mole fraction of A in the liquid phase, right? We typically use X to denote it, or the mole fraction of A in the gas phase. We typically use Y to denote it for this, right? And in these different functional forms, the mass transfer coefficients will have different units, but they can be easily converted easily, okay? Okay, so that's all for the mass transfer coefficients. Any questions? Okay, if not, we can just move on to the next topic. So we're gonna do a brief introduction to the thermodynamics review, and hopefully we'll finish this thermodynamics review in our next lecture. So I mean, thermodynamics, we've learned the concept of the state, right? And in reaction engineering or reaction kinetics, you've learned the concept of rate, right? These are two different concepts. And thermodynamics only tell us, thermodynamics only concerns system at equilibrium, in which we describe our system using states, right? Which is concept. But does not really tell us how fast we can move from one state to another, right? This is like similar to if you look at a motion of an object, for example, or projectile from a gun or cannon, then energy balance tells you where the projectile will end up be, but doesn't tell you how the movement will happen, how the trajectory will happen. That kinematics will tell you that. So in in chemical engineering, thermodynamics similarly will tell you, your system where your system will end up be at equilibrium, but doesn't tell you how fast your system will move from state A to state B, right? In order to answer that question, how fast our system can move one state to another, we need to look at the mass transfer and the reactions, right? That will take you from state 1 to state B. So the transport is basically the mixing process, which can happen due to a diffusion or convection. And kinetics is how fast reaction happens, and it's a rate at which reaction occurs, and to between two equilibrium states, right? So in reality, there are a lot of cases where thermodynamic equilibrium predicts one thing, but if you look at it, the real example, it never happens, right? For example, we know that carbon has different polymorphs, right? Which includes amorphous carbon, includes graphite and diamond. But thermodynamically, graphite is the thermodynamically most stable form, right? But still, if you get a diamond, it doesn't change to graphite overnight or over like a course of several years. Otherwise, people would not buy diamonds, right? That's because the transition between from diamond to graphite is basically fundamentally limited by how fast the carbon atoms can move around, right, in a solid state, which we know is extremely slow, right? We talk about diffusivity, and we know that diffusivity really depends on the density of your phase. And we talk about gas phase will have higher diffusivity in the liquid phase. And the same is true with solid, right? The liquid phase will have a higher diffusivity in the solid phase. Okay, so that's why the conversion between diamond and graphite is extremely slow, so that people buy diamonds. Similarly, in our body, we have a lot of like organic molecules, right? Glucose or DNAs, proteins. All these biomolecules, they actually contain a lot of energy, right? If you burn them in air, they will release a lot of energy. But we are still human. We don't become CO2 and water. That's because the reaction in our body, right? Our metabolism of the glucose or other organic molecules are controlled in our body by the enzymes and by our by our body function, right? We don't, but after an animal dies, over time, the body will decay and eventually become CO2 and water. Okay, so in chemical engineering, sometimes it's convenient for us to really describe the system we are interested in if we can make an assumption that our system is at equilibrium, because in that case we don't have to deal with the very complex transport of reaction stuff. Typically for most unit operations, we can make that assumption. We can assume all the phases are in equilibrium, as long as we have a well-mixed system and we have we have sufficient resonance time. Okay. Okay, I think we're gonna stop here. Then next lecture we're gonna talk about the conditions for phase equilibrium.